Yeah, thank you for hosting us here. And right now I'll be presenting about the Cornell Hyperloop propulsion system design for this year. Well, first I want to start with the system overview. We are implementing a linear induction motor powered propulsion system. We outsourced the linear induction motor from the H2W Technologies company. That I believe somebody in the competition is also planning to use this supplier actually. Yeah, the whole system is powered by our custom on-board battery pack, and the control and the inputs are controlled. In the inputs to the linear induction motor are controlled by the variable frequency drive, also on the pod, and that will be using during the testing phase. Additionally, we implement some sensors on the pod to gain the current values for the speed and acceleration of the pod, and use them in a closed loop control system. And additionally, we have the cooling system, because the linear induction motor gets very hot and we need to make sure that it doesn't overheat, that it doesn't burn the wires, for example. So we have a cooling system, the liquid cooling system implemented for that. And the last step in our design process is implementing the electromagnetic interference shielding to protect the electronics on the pod from the magnetic field due to the linear induction motor. Well, first I want to go into the working principle of the linear induction motor and some of its internal components. Well, the linear induction motor consists of the core, that is the ferrous material, usually it's iron, and additionally it has three phases of wires wrapped around the teeth of the core. Well, the three phases have the exact same magnitude and frequency, but they are sinusoidal signals offset by a phase of a third of a period. So this, combined with the geometry of the linear induction motor, generates a moving magnetic field that induces a time-varying magnetic flux into the I-beam, which generates, once again, the eddy currents, and this results in the propulsion of the pod. The linear induction motor can be represented with the following magnetic equivalent circuit. There are multiple papers, and they have slightly different approaches to this. This is one of the options, and I went with this one. In this case, the current in this circuit models the magnetic flux of the track and the linear induction motor. The resistances in this circuit represent the reluctances of the track and other components of the system. And the voltage source in this case represents the wire that has the current running through it. So knowing this circuit, and we can derive and find dynamic equations that would allow us to relate the input to this circuit, that is the sinusoidal voltage, to the outputs, that is the thrust and speed that are generated for our pod. As for controlling the propulsion system, we are implementing a voltage frequency control. It's a pretty classical method. Once again, yeah, the whole system is powered by the DC battery pack on board of the pod. Then the VFD takes in this power, converts it to the three phases of AC currents that are the inputs to the linear induction motor. And by varying the voltage and frequency, we can get the speed and thrust desired in our scenario. And the general rule of thumb is that high frequency results in high speed of the pod, and high voltage results in high acceleration of the pod. Here's the control scheme that we'll be using. We might be improving it after that, but this is like one of our initial versions. First of all, we input the reference speed that we want the pod to achieve, for example, 5 meters per second. We compare it to the actual speed of the pod. Then we calculate the difference between these two values. This difference goes into the PID controller, that's the proportional integral derivative controller, and I'll go a bit into it in the future slide. Then we do some calculations with these values, and we get the exact phases, frequencies, and voltages that we need to input into our linear induction motor. After that, knowing the system dynamics, we can calculate the acceleration of the pod and get the speed of the pod as a result. And after that, the loop continues, and we continue checking our speed against the reference speed, and therefore we can adjust our controls continuously as to what we need to supply to the linear induction motor to achieve the desired result. Additional controller requirements in our case include the 20% maximum overshoot. That is, if we apply a step reference input, for example, going from 0 to 5 meters per second, our speed doesn't go too high initially when it balances out to the steady state. And the second requirement is that we have the 0% steady state error, which means that when we are cruising, we are traveling exactly at the speed that we want to achieve. So the difference is 0 between the two values. The fundamental parameters of the control scheme are the proportional gain, integral gain, and derivative gain. That is Kp, Ki, and Kd. They each have different effects on the dynamics of the system, and they affect the performance of the system in various ways. And it's our job to tune these values specifically to achieve the desired performance. For example, graph on the right, it has one of the example responses of how the system may perform. That's the velocity against the time graph. This graph utilizes absolutely arbitrary values, but this is approximately or similar to what the dynamics of the pod might look like as a result. And then we can, for example, integrate the velocity of time and get the exact position of the pod so that we can brake at the needed moment. Okay, a bit more about the controls. There is really a comprehensive plan that's required to implement the control system, and it involves 4 general steps. The first step is to implement the so-called black box limb testing procedure to characterize the linear induction motor circuit. Well, as you can see, it has some resistors, some inductors in it, and we want to find the value of each of those parameters. So we can find the dependence of the thrust and the speed of the motor from the input. After that, when we found those parameters, we can implement the MATLAB Simulink model. That is, we'll get our linear induction motor model. And after that, we can use it in our control algorithm, and through simulations, we'll be able to find the exact gain values, that's Kp, Ki, and Kd that we need to achieve the required, the desired performance of our system. And after that, when we are confident that our approach will work, we can finally implement the system in real life. Well, as for the black box testing, first of all, it's important to simulate the track for the pod. Well, when the pod is moving, we would have the linear induction motor that's moving with respect to the track. But in the testing procedure, it's quite the opposite. It's the track that's moving with respect to the linear induction motor. We don't really have a space to put a track on canvas, so that's why we simulate the track by a rotating flywheel, effectively. That's a quite classical approach, honestly, to this test, and that's what we decided to go with. We have 3 testing cases. That's the RDC testing, no load testing when the flywheel is free to rotate, and the infinite load testing. That's when the flywheel is locked and it cannot rotate at all. Well, each of these tests gives us different values for our linear induction motor model, and then we can use these values to finally implement the motor. Here, for example, is the electrical circuit that we'll be using during those tests. In the RDC testing, we supply DC voltage directly from the battery pack to the linear induction motor. And in the no load and the infinite load testing, we supply DC power to the VFD, which converts the DC power into the 3 phases required for the linear induction motor to operate in those cases. As you can see, we also have a thermal switch inside of the motor. Well, what it really does is the thermal switch controls the temperature inside of the linear induction motor. If the temperature gets too high, the circuit opens. And in our case, the power is cut off to the conductor, so the circuit also opens, and the power is not coming to the linear induction, and the power stops coming to the linear induction motor. So this essentially would allow us to save the equipment from overheating. And this will also be implemented on board of the pod. Okay. And now a small bit about mounting and the cooling of linear induction motor system. Well, we're using a very simple lateral mount that's bolted to the chassis of the pod with the angle brackets. Well, in our case, the chassis are also very simple but convenient for mounting all the system on board of the pod. It's really just a ladder type structure, and it just makes the mounting and the fabrication of the chassis very simple and very cheap. As for the cooling system for the linear induction motor, the limb can get very hot, actually extremely hot, and for that we need to somehow cool it down. For that we decided to use the liquid cooling system with water. Essentially what I decided to implement is to have a double heat exchanger with the chassis. First of all, the water is being heated up by the linear induction motor, then cycles to the chassis, gives off the heat to the chassis, and then the heat is cooled with the air that's passing through the chassis. As you can see, the chassis are hollow on the inside. So, for example, cold air can go through the chassis and cool down the chassis and the water as a result. Okay, and here's some of the analysis that I did for the cooling system. Well, I'm really analyzing the chunk of water that's passing through the system. And specifically, I'm getting the temperature profile with time. The trajectory of water would be to start at the cold heat sink in the state 0, then it passes to then along the tubing of the pod, it passes to the hot heat sink on the linear induction motor. It heats up, getting all the heat from the limb. Then the water returns back to the chassis where it cools down, and the cycle repeats many times. Well, by doing a differential analysis on this chunk of water that's passing through the cycle, we can get the differential equation. And by solving it, we can get the temperature profile with time, as I said previously. And on the bottom left corner, you can see an example of how this profile may look like. So, for example, it starts in the 0 state, it heats up, then as it's traveling through the tubes, it's maintaining the temperature, entering the heat sink on the chassis, it's cooling down, and etc. Once again, the cycle continues. So a big part, perhaps, of this process is to estimate the coefficients of thermal convection between linear induction motor and the aluminum heat sinks, between the aluminum heat sinks and water. And there are additional testing procedures that are required for this. But with the current coefficients that we just estimated, I was able to find that this system should be able to cool the linear induction motor by about 4,000 watts. So that's 4,000 joules per second. This approximately equals the amount of heat that I expect will be generated from the linear induction motor at the 50% efficiency. So thank you so much for listening. And if you have any questions right now, is the best moment to ask them. I'll try to answer them to the best of my ability.
New comment from Alex. Which three-phase controller are you using for the limb?
We have not decided on it yet specifically. We have picked the VFD that we will be using. The VFD, it has manual inputs and it has digital inputs. So we plan to, I believe there is just a bus that's coming there is a bus with data that's coming within the VFD and the controller. In general, our pod, I believe, will be controlled by the combination of Raspberry Pis and Arduinos. So they'll mostly govern the inputs to the VFD.
I have one question, that the proposed model for cooling system for the linear induction motor.
Yes.
Have you any simulation proof for that, or any practical approach is there, or it is still a theoretical concept?
Yeah, right now it's a theoretical concept. We'll definitely do testing pretty soon. Really just trying to, well, when we'll be testing the linear induction motor, we plan to get exact temperature profiles of the linear induction motor with time, so we can get the exact heat that's generated during the operation. And from that point, we'll be able to do more precise testing and have a more precise model with the values. So testing will only start in the following few weeks.